Hello and welcome. In this video, we'll be discussing the Way ANOVA, which is an analytic approach that allows us to account for multiple independent variables when looking at the outcome. So one of the coolest aspects of ANOVA is what we're talking about in this video. That is that it can handle multiple independent variables. This lets us do a couple of important things. First, I can analyze two or more independent variables, which sounds good at the outset, but it also lets me look at how one of the levels, or one of the independent variables, the levels of that variable, can influence the relationship between the outcome and the other variable. This term is called interaction, and it's something that you probably haven't seen before, but is a really important concept when considering problems with multiple variables. So we'll discuss it a little bit in this video, and then we'll discuss some more in future chapters. Now you'll note Way ANOVA, these tests have a number of ways associated with them. The Way ANOVA simply represents that we are using two independent variables in the analysis. So a Way ANOVA represents we're using one independent variable. A Way ANOVA would represent that we're using three independent variables, and so on and so forth. Generically, in an ANOVA with multiple independent variables, you'll hear it called a factorial ANOVA, an ANOVA with multiple independent variables generically. So we're not trying to talk about Way ANOVA. I'll mention that the ability to count for other independent variables is useful, but we don't always have to care about the other variables that we include. So for instance, it may be useful to include other variables just to account for their impact on the outcome, as opposed to because we particularly care to study that. So for instance, if I'm looking at the relationship of variable 1 on the outcome, but I know a second variable also influences the outcome, I might include that second variable even though that's not what I'm trying to study, just to make sure that that second variable's relationship is taken into account. This relates to the conclusion changes that happen with ANOVA. So I don't know that I have this on the slides, you may need to write this down, but when I do the interpretation of a Way ANOVA and interpret the results of one of the variables, the results of that variable are now significant after accounting for the other variable. And so that introduces why this is useful to account for other variables, even if you're not interested in them. If I'm looking at the relationship between a variable and the outcome, and I know a second variable is also important, it might be useful for me to know and to be able to describe to others that I'm looking at the relationship between the variable I care about and the outcome after accounting for that other variable that everybody knows is also important. So the change in interpretation is what really drives inclusions of other variables sometimes, even other variables that we don't particularly care about in our study. So the concept of interaction is an immensely important idea in analysis, especially when dealing with multiple independent variables, though it is a bit tricky. So being an old math teacher, let's look at the graphic of ACT math scores made up, and we're going to break this down by race and gender as the independent variables. And to keep it simple, I'm just going to use two races, black and white, B and W respectively, and two genders, male and female. So in this case, you'll see the male line is orange, the female line is purple, the black race is indicated at the beginning, and the white race is indicated at the end. You'll note that the height represents the height in terms of ACT scores. So a higher ACT score represents a higher dot. The question is, and I want you to think about this, are black students doing better on the ACT than white students? Are males doing better on the ACT than females? Well, in those questions, ultimately the answer depends on the level of the other variable. Are black students doing better than white students? Well, if you're a male, yes, on average, black students are doing better than white students. On that orange line, the dot for B is higher than the dot for W. On the female line, though, black students are doing worse than white students. The dot for B is lower than the dot for W. Are males doing better than females? Well, it depends if you're black or white. If you're black, males are doing better than females. The orange dot is higher than the purple dot in the B column. But if you're white, Males are doing worse than females. The purple dot is higher than the orange dot in the white column. The reason I present this is to explain how the interpretation of a simple question, are black students doing better than white students on the ACT score, or are males doing better than females on the ACT score, in the presence of an interaction can have a complex interpretation. The interpretation depends on the other variable. If you're asking me about sex or gender, well, it depends on the race. If you're asking me about race, it depends on the sex or gender. And that "it depends" is the definition of an interaction term. If the results for the effect of one variable, independent variable, depend on another independent variable's values, those two variables are said to have an interaction. You'll note that because of this, when we have an interaction effect, we can't provide simple explanations. So the effect of race, say, that's called a main effect, where I just look at the effect of the independent variable by itself. That's not really interpretable. I can't say black is better than white or white is better than black on the ACT score on average, because it really does depend on something else. Same thing with males and females. I can't say males are better than females on the ACT score on average, or females are better than males, because it really does depend on the race. So in this case, I can't do simple interpretations. I can't do a simple interpretation for race, and I can't do a simple interpretation for gender here. Instead, if I wanted to interpret these results in the presence of a significant interaction, I'd have to pull up a plot that looks kind of like this. This plot's called an interaction plot, and it's used to demonstrate the conditions where each group is more successful in this ACT score example. So now that we've talked about an interaction, this actually introduces a new process of analyzing our data. This is kind of a data analytics workflow, if you will. And so the steps are: we read and enter in the data, we fit the appropriate model, and since we're in the ANOVA chapter, these examples, the appropriate model is ANOVA, and then we check the assumptions. Now, if the assumptions fail, we don't continue. If we can try to fix them. And if the assumptions pass, we continue. I will note we haven't touched on the assumptions much, but when we get to the end of this course, we will talk in depth about checking assumptions, and this is where those would go. Now, after we fit the appropriate model, and again, in this particular video, we're kind of skipping assumption checks, but after we fit the appropriate model, we first check the interaction term. So if there's a significant interaction, like on our previous graph, there was a significant interaction between race and gender, we would say, look, there's a significant interaction. That means we can't just interpret race or gender, because it's more complicated than that. So first we check for an interaction term. If there is a significant interaction term, we stop and we create a plot, like the interaction plot we looked at earlier, to check and interpret the effects in the context of the other variables. If there's not a significant interaction, we go forth and we interpret the main effects. So if there wasn't a significant interaction between, say, race and gender, what that would imply is it doesn't really matter what your gender is. You know, the race has a consistent effect. Maybe black students are doing better than white students on the ACT for both males and females. It didn't depend on the other variable. And in that case, it's completely sound to interpret that variable, the race variable, that black students are doing better than white students on the ACT. But note that I can only do that if there's no interaction effect. I can only do that if the interpretation doesn't depend on the other variable. So if there's no significant interaction term, I can go on and interpret those main effects. As I mentioned before, the interpretations of the main effects when we do a two-way ANOVA is now after accounting for the other independent variable. So I've got my independent variable A, and I'm looking at the relationship between that. Again, we'll call it race, and looking at the interpretation of that, or the effect of that on ACT score. And I want to do that after accounting for the individual's gender. So I would include gender, and then if there's no interaction effect, I can interpret race, and the interpretations of race, significant or not, would be after accounting for gender. And of course, if there is an interaction effect, I simply make a plot and then interpret that interaction plot. Now, with a new variable, we have to update our notation to account for the fact that there's a second independent variable. I equals 1 to capital I will still represent the levels of the first IV with capital I, total number of levels in the first variable. But now J is going to change meaning. J previously was the number of observations, but now J is going to be the levels in the second independent variable. Capital J is going to be the total number of options for the second independent variable. So if I were doing race and gender, in my example, I equals 1 to 2. There are 2 total race groups, and J equals also 1 to 2. There were 2 total gender groups that were considered. K is a new variable that we're going to add because now we don't have anything to account for how many observations we have. And K is going to represent the number of observations from 1 to capital K, which is the total number of observations in each group. Now, when I say in each group, we're thinking in each cell. So that would be the total number of male or black male students, the total number of black female students. So in each of the combinations of factor level categories. That can sound fancy. I tried to put together this graph to visualize. I realize this may be a bit counterproductive. It looks a bit complex, but hopefully this does help. In here, you can see the first independent variable. The columns go from, or excuse me, the rows go from 1 to capital I, the total number of levels in the first independent variable. The second independent variable goes from 1 to capital J. Those are the columns. And that's the total number, capital J is the total number of levels in the second independent variable now. Again, that's a change. And in each combination of these things, again, the first one you can interpret as black males. The top right you can interpret as black females. The bottom left would be white males. Or excuse me, the top right would be white males? I can't remember. And in any case, you'd have black and white for your one variable and males and females for the other, and where those things meet, that's both of them at the same time. And 1 to capital K represents how many of those meet. So again, how many black males? That would be capital K. And assuming each of the groups are still the same size, you'd have the same number of black males, as white males, as black females, as white females in your sample. And again, the number within that particular cell, the number of black males is capital K. The total number in the total study is capital N. Just like before, sometimes we use lowercase n instead of capital K to refer to the sample size in each of those cells. All right, well, data format, depending on what's covered in the review and what's covered in your previous course, and depending on if you looked, I think we talked a little bit about data format, depending on maybe in one of the first R lectures, I can't remember. But the data format is something that actually comes into play here in ANOVA pretty strongly, because the data format has to be formatted in a certain way for the data to be analyzed. Now, this is software dependent, so different software require different formats. So you'll have to check with your software. In R, the data format has to be structured as a long format, and the data format of the table I showed you previously is not convenient. So when we list each level of the variable, or a combination of levels, as a separate column, so males is column 1, females is column 2, or combination of variables would be white males is column 1, white females is column 2, black males is column 1, black females is column 2. When we do it like that, the data are called wide data. That is, as I continue to add more factor levels, the data get wider and wider and wider. Alternatively, what we can do is each factor is listed as its own column. And I'll show you a visual example in a second, but I might have a column for race, a column for gender, and then a column for the ACT score. And so for each individual, I'd write what's your race, what's your gender, and then what's your ACT score. As you add more and more factor levels to that, let's say I considered other races, let's say Hispanic was added. Instead of getting wider and wider and wider, this data would get longer and longer and longer, so it's called long format. Here's a great visual example. I think I pulled this from online somewhere, but wide format, we have team A, B, C, D, and then points, assists, and rebounds. In the long format, I'd have, instead of the wide points, assists, and rebounds being the column levels, I'd have something named, say, variable or statistic, and then I would include those different levels going down. So we'd have team A, and then the points, assists, and rebounds. And then we'd have the value 88, 12, and 22 going down instead of going across. So the wide format versus the long format. Now, the ANOVA table is going to look very similar to what we had before with two additions. You'll note the second row is an addition. Now we include the second variable, but if you read across, this should look very, very, very similar to before. The sum of squares for variable b, the degrees of freedom for variable b. The sum of squares for variable b divided by the degrees of freedom for variable b. And then the mean squares for variable b divided by the mean squared error. We also, though, include a row for the interaction term. So this will have its own sum of squares, degrees of freedom, mean squares, and F statistic. You'll note that we calculate the F statistic for variable A, variable B, and their interaction, as well as the p-values, testing for significance on all of them. Recall the workflow, once I get the table and have set everything up correctly and checked assumptions, is that I'm going to look at the interaction first, and then if that interaction is not statistically significant, check out the significance of variable A and B and interpret those. The equations are going to look somewhat familiar, and I'll be honest, I don't use these equations very often because I just use software to fit the models. That's what we'll teach in this course. But if you're interested, you'll note that the fill in the blanks are on the left side. I don't make you fill in all of these blanks because some of these equations are yucky, but this is the equations for the sum of squares A, sum of squares B, sum of squares for the interaction, the sum of squares error, and the sum of squares total. Again, we have to add over all of the values in variable A, all of the values in variable B, and all of the individuals in the combination A-B cell. For the degrees of freedom, similarly, we can calculate this. Degrees of freedom for A makes sense, the number of levels in A minus 1. The degrees of freedom B should also make sense, number of levels in B minus 1. But once we get to the interaction, things break down a little bit. You'll note that I changed notation. Here I'm using lowercase n instead of capital K. And remember, you can go between the two. So if you prefer to use capital K there, that's fine. Or if you prefer to use lowercase n, that's fine to represent the total number of observations within that particular grouping of cells. So again, I don't typically do these by hand, and we're actually in the lecture notes not going to do one by hand. But these are there. So if you want to do it, go knock yourself out. All right, so let's check this out. This is kind of an interesting problem. We're looking at battery life, but in batteries, each of these battery brands actually offer two different kinds of batteries. We can buy alkaline batteries or lithium batteries that we're testing in each of our products. So we're still looking at the number of hours, but now we have multiple factors. We have the brand that we're assessing with levels D, E, and G, and we have the metal type, the alkaline and lithium. The experimental unit is still the individual products, and our outcome is still the hours that the product lasts. Now, this is the weird wide form. What I would do if I were doing a long form is have a single column for metal, a single column for brand, and then I would enter each of these numbers. So for instance, the top left number, 67, that entry would look like the single column metal would have the letter A in it for metal A. The second column, brand, would have the letter D in it for brand D. And then the third column, hours, would have the number 67 in it to represent the first product was with the alkaline metal and the Duracell brand, and it lasted 67 hours. And then for each one of these, I would just add a row to that. So for instance, in the bottom left, the next, if I were at that row, the metal would read L, the brand would read D, and the hours would read 70. And I would just keep going with all the rest. So it's worth noting in this situation, now when I add a second variable, I actually get 3 tests. So I add one variable, but add 2 tests. The first variable, all brands are the same. Remember, brand is factor A. And then the alternative is at least one brand is different. Not one battery, one brand, excuse me. For the second test, all metals are the same, and at least one metal is different. And then for the third test, the test of the interaction, we'd assume by the null hypothesis that there's not an interaction, and a significant finding would be that there is a significant interaction. All right, so first, when I enter the data, I have to write it in long format to be analyzed in R. In fact, I don't know, given that previous format, that any software would analyze the data natively in that previous format. So you're going to have to reformat that information somehow. So we format into long form, and then we plug it into R. R is going to give me the following ANOVA table. And again, I'm not calculating the sum of squares or anything like that by hand, though I will mention for the individual main effects, that is the brand and metal, not the interaction, for the main effects of my two factors, I do usually check the degrees of freedom, because remember, it's the number of groups minus 1. So I expect the degrees of freedom for brand, there were 3 brands minus 1, the degrees of freedom should be 2 in that first row, and I see that that's true. For metal, there were 2 metals. 2 minus 1 is 1. The degrees of freedom should be 1 for metal, and I see that that's true. So that's a good way to double check that my table is reading appropriately. Can also double check the total, make sure I anticipate that I have 30 total observations. The total degrees of freedom should be 30 minus 1, or 29. Again, for the total observations, not the total in each cell. All right, so now I interpret my results. My first interpretation is of that interaction row. So remember, I ignore, even though they come first in the table, the first 2 factors and jump straight to the interaction first before doing anything else. Remember, if the interaction is significant, I'm not going to do the other ones. And if the interaction isn't significant, then I can go on to interpret the other ones. Looking at my interaction term, there's no statistically significant interaction. So I'm looking at that P, seeing is it less than 0.05? It's not. So there's not enough evidence to determine that there's an interaction here. Remember what interaction means if you're wanting to get a little more out of this in terms of the interpretation. Interaction would mean that the different brands differ in effectiveness based on the metal. So maybe Duracell has a better lithium battery. Energizer has a better alkaline battery. That is, the metal affects which brand is best. In this case, again, there's no interaction, so that's not the case. The brand effectiveness doesn't depend on what metal it was made on. And again, that it depends is the interpretation, and that's how I interpret it at the interpretation step 2. The fact that there's not an interaction means that there's not enough evidence to determine that the brand effect depends on the metal, or that the metal effect depends on the brand. In this case then, because there's not an interaction, I can go on and interpret the main effects, that is, the effects of factor A and B by themselves. So interpreting brand, I know that brand doesn't depend on metal, but it does appear that brand is significantly different. That is, there's a statistically significant difference between those brands. And remember, the interpretation now that I'm doing a two-way ANOVA, is not just there's a significant difference between the brands, but there's a significant difference between the brands after accounting for the type of metal used in the battery. For the metal, when I read this, there's not a significant effect in the metal. And again, for the brand, I'm comparing P to alpha. So P is a very small number. It's less than alpha. That means there's a significant effect. For metal, P is a large number compared to alpha, 0.05. P is bigger than alpha, so there's not a significant effect. That is, there's not enough evidence to determine that battery life on average depends on the metal used, but there is enough evidence to determine that battery life depends on the brand. Again, there's a statistically significant difference between the brands and their performance in terms of hours. So yeah, brand is significantly different. The type of metal is not significantly different. And we can perform post hoc tests with each of these variables as needed without worrying about how they impact each other. So I can look at brand and I can perform an analysis of the brand without worrying about accounting for metal because my interaction was not significant. There wasn't enough evidence to determine that the brand effectiveness depended on the metal. So I'm not going to worry about the metal. I'm just going to look at the brand effectiveness with my traditional post hoc test methods. Now, this is a bit out there, but I will make a quick note here on something called a randomized complete block design, RCBD. If the second independent variable is a blocking factor, we look at this situation slightly differently. So remember, a blocking factor is something that we want to take into account, but we don't necessarily care about. And specifically, we kind of talked about this previously, like if we're looking at something like a piece of wood and wood joints, and I make wood joints and I can only get 2 joints in a single piece of wood. So I want to take into account which piece of wood I'm using. It's not that I really care about it, but it's there. First, we can note the randomized complete block design is a design, not an analysis. So when I talk about this, hear that this is a design concept, not an ANOVA. Not an analysis. The analysis for a randomized complete block design is ANOVA. That's slightly modified from what we've done previously. So the block, if it represents a limit on randomization, so think about this. I can't randomly assign the ends of a board to a different board. So if I'm accounting for board, I can't randomly assign that to something else. So the board itself is a limit on randomization. What I do then, let's say I'm testing the dovetail joint and the butt joint on a particular board or a bunch of boards, because I can't randomly assign the end of a board to a different end of a different board, what I do is I randomly assign the one that I can control, the joint, to each end of the board. So I randomly assign within the block. So within the board, I'll randomly assign. So for board 1, I'll randomly assign butt joints this side, dovetails on that side. And then for the next board, inside the block, the board, I'll randomly assign. So because of this, the boards or blocking factors in general can represent a limitation on randomization. And in that case, we approach randomization slightly differently. But what this means is we didn't randomly assign things to different boards. So the board is an observational thing, even though the joint is a randomized assignment thing. Because of this, we tend to not interpret the main effect of the block because we didn't do random assignment, though we do still include it to account for the fact that different boards may have an effect. So this is included as one of those factors that's there, but we're not really going to worry about. Because of this, the additional thing that I want to note specifically here is that we also don't include the interaction. We're not interpreting the main effect of the block, and so we're also not going to interpret the interaction with that blocking factor. With that said, the interaction of the main effect is still the same as in the two-way ANOVA. So when I'm studying the joint, I still get to interpret the joint, and I get to say things like interpretation after accounting for the board it was done on. All right, so how do we write up one of these two-way ANOVAs? Well, again, often this is accompanied with an ANOVA table. I like to do graphics with this. I didn't mention in the earlier APA write-up, but graphics are also a really handy thing to include in reports, whether you're reporting it in a journal or reporting it to a colleague or a boss. Everybody loves graphics. Again, graphics, though, are subjective, so it's very important if you present a graphical method to have statistics like an ANOVA to back up differences between box and whisker plots. And then we would potentially do post hoc analyses here. But again, just for the sake of time, we'll present our two-way ANOVA, just the ANOVA part. So we could mention what we're assessing, the average hours of battery life. We've got our variables, the manufacturer and the metal. We've got the level. And then we just say there's not enough evidence to determine that the metal was related. You'll note that each of the F tests, I use the degrees of freedom 1 for the numerator. So for the test of metal, the degrees of freedom 1 is the degrees of freedom of the metal variable, and then the 24 is the degrees of freedom of the error. So I've got my test statistic, and then I've got my p-value for that test. Go on to say there was enough evidence to determine the manufacturer was related to battery life. And again, the first degrees of freedom is the degrees of freedom from that factor. So from the battery life factor, the degrees of freedom was 2. So F2, 24 still coming from the degrees of freedom from the error. And then I have my test statistic and p-value. Finally, I mentioned that there's not enough evidence to determine a significant interaction between the two. And then I would go on potentially to include a table or include a graphic. And then depending on the writing format, I might talk about what this means at a practical level. What does this suggest that we should do as a decision? All right. Well, that takes us to the end of our ANOVA lecture. So this is the end of our ANOVA lecture set. Thank you so much for sticking with me through this. Of course, this content is followed by a demonstration of how we can implement these analytic methods in software. So please stay tuned for that. But otherwise, I'm sure you're probably glad to be over this. This is fun. This is a very useful method. This is something that's used often. Again, in those experimental designs, we do this method pretty often. It's probably one of the more common ones we'll learn about in class. And it's just because it is so broadly applicable. So I hope you learned something. I hope it was fun. Again, thanks for sticking with me through this video, and I will look forward to catching you in the next one.